Okay, greetings aspiring scientists. Welcome to my video today on Introduction to Intermolecular Forces. I think we'll get into London dispersion forces, dipole-dipole forces, dipole-induced dipole forces today, and probably leave hydrogen bonding for a different video. So let's get into it and go to my slides. So this is 2.2.8 in the IB curriculum, the IB syllabus. So you might notice if you're watching my videos in order that I skipped 2.2.7. I think this is probably the only case where I'm doing things out of order from the IB curriculum or the order of most textbooks. But I really think intermolecular forces need to be taught before, what's the other one? Networks, covalent networks. Because there are things to understand about networks that we can only understand if we know about intermolecular forces. Okay, so let's get into it. Intermolecular force types. There are several that we need to know. Intermolecular forces refer to interactions between molecules. Okay, this is really the first time I think that we're talking about this in my videos. We've talked a lot about what holds molecules together, chemical bonds, chemical bonding. This is not what this is. This is not what we're studying today. We're studying how molecules interact between each other. So intermolecular forces are weaker than intramolecular forces generally, but intermolecular forces determine most of the physical properties of matter. What shapes it takes, whether it's gas, liquid, or solid, its boiling points, melting points, its strength, those kind of things. So it is hugely important to study for materials science. So there are three main types I think we'll study: London forces or London dispersion forces, dipole-dipole forces, and dipole-induced dipole forces, and hydrogen bonding. As I said, I think we'll get to the first two in my video today. So let's be clear about intra versus inter. Intramolecular force do exist, but it's just like a chemical bond, things that hold chemical nuclei together. So on the left here, I'm pointing to intramolecular force, a covalent bond between H and F in the molecule HF. It is a polar molecule, yes, but the chemical bond between H and F, we can call an intramolecular bond. Okay, it doesn't really have much to do with actually the behavior of the material. That behavior is going to come from the intermolecular forces. So on the right here, we have intermolecular force between two HF molecules. You'll notice that the negative region of one is approaching the positive region of the other, and there's a dotted line that shows some kind of attraction or interaction is happening. So this is not a true bond. It is an electrostatic type of attraction between polarized regions on both molecules. And that's going to be the key of all of the force types that we're looking at today. Okay, so I want to just go through some notation here. London forces, dipole-dipole forces, and hydrogen bonding. These are the three types I've introduced to you. Now it turns out London forces and dipole-dipole forces can be grouped into another category called van der Waals forces, and in fact I actually see this labeled more often, especially in media from like the US or Canada. I think van der Waals forces maybe is used a little more than London forces and dipole-dipole forces, but for IB we need to know the separation between these, and I have a little greater than or less than sign here. So London forces are generally weaker than, dipole-dipole forces are weaker than hydrogen bonding. So you can also say van der Waals forces are weaker than hydrogen bonding. And I've also included in here dipole-dipole forces has a subset that we're going to call dipole-induced dipole. We'll get to that soon. Okay, seemingly random, but you might remember this graph from one of my previous videos about ideal gases. This shows the deviation of ideal gas behavior from the normal. Okay, normally we would have PV equals nRT, so N equals PV divided by RT. Maybe I can draw that here. So the equation that's in your data book is PV equals nRT. So you can just rearrange this for n. N equals PV over RT. That's what we have on the y-axis of this graph. And we're going to say that we're working with 1 mole of gas. So whenever we multiply the pressure and the volume and divide by R and the temperature of this gas, it should always be equal to 1. It should be equal to N, and we just have 1 mole of gas here. But what I've told you before is that real gases are not ideal gases, and under different temperatures and pressures, they may and will start to behave non-ideally, and that means that this graph will not give a y value of 1 all the time. Okay, so it's really the temperature effect of this graph where we see different temperatures, 150K, 500K, 900K. These have significant differences from each other and differences from the expected straight line of 1. PV over RT equals 1. All of these are fairly deviating from that, and these are the temperature effects. So as we get lower temperature, 150 Kelvin, that's like over 100 below zero, right? Well, this curve is the most deviating. Why is that? Well, as the molecules slow down, they start to feel the forces of each other, of other molecules nearby, much more. Similarly, how I explained it in my previous video is if you have a magnet on a desk and you throw another magnet nearby it, the faster you throw that magnet, the less effect it's going to have, the less change you're going to see in any of their paths. But if you throw it slowly, slide it slowly, there's more chance, more time nearby for forces to act, and you get more deviations in the path. Very similar thing happening here. Lower temperature means more intermolecular forces. We haven't even learned really what they are yet or how they come to be, but you should know lower temperature has more intermolecular forces. And that's especially important when you're trying to consider if a gas is ideal, behaving ideally or not. Okay, moving on. So, London forces. This is the first one we'll talk about, and we'll talk about the idea of polarizability. So, something we have to understand here is that London forces happen for all molecules, all atoms, all compounds, but they have widely varying strength. Generally, they are low for low molecular weight compounds. So how does it work? Let's imagine just a hydrogen H2 molecule. You draw that in yellow here. H bonded with H. These each bring 1 electron to this bond. But these regions are just probability of where electrons might be found, right? So if we just take a snapshot of this at any time, we might have an electron there on the left one and there on the right one. And this is fairly balanced. The electron isn't really on one side more than the other. There's not more density above or below more than the other. We might take a snapshot of this again after some time t. The electron moves around. What are we going to have? Could be anything really, but maybe I'll just say the electron is more on the left now, more on the right. This is probably a less likely state because they're not in between the nuclei, but still it's very balanced. In terms of up, down, left, right, there's not more electron density one way or the other. But every once in a while, you might have something like this. take another snapshot. 2 electrons in between the nuclei, so that's likely, but they're closer to one hydrogen than the other. Just by random chance. Electrons have chance to be basically anywhere, just more chance to be in some areas sometimes. I know that's confusing, but there's nothing that says we can't group up electrons like this sometimes. And I should say, this is me sort of going based off my own knowledge. I don't think this is actually exactly what happens, but it's the way that I remember how to judge London forces and explain them that generally works, so I think you can do the same. So in this snapshot, what has happened? Electrons are more on the right side than the left. So this actually has a dipole, a negative dipole towards the right side, and a positive dipole towards the left. Electrons have left the left side a little bit. And that was after some other time t. And okay, you might check that again after another time t, and it goes back to basically what it was at the start, maybe just reversed positions. Random, but highly probable formation of these electrons. But it's really this third one here that will cause attraction between H2 molecules, even though there is no permanent polarity in the molecule. This is how nonpolar molecules are generally attracted to each other. And you might say, well, if the chance is small for that, are they ever going to be near another hydrogen that's polarized this way for a very short time? And is the attraction going to be significant? So this is where the idea of induced dipoles comes in. Okay, it only actually takes one hydrogen like this to affect all of the hydrogen molecules around it. So I have a little animation here. We've got what's called the instantaneous dipole. That's what I just showed in the circled diagram here. Randomly, electron density flows more into one region than the other. Unlikely and very short-lived, but it can create induced dipoles on hydrogen molecules around it. Let's see if we can see that. So the instantaneous dipole actually causes electron density in nearby molecules to shift because of its own shift, right? It gets polarized negative and positive on one side, and it will make nearby molecules polarized just by approaching them. And that will create an attraction because you've got negative near positive, positive near negative. So this requires a bit of freedom in the electron movement in the molecule, right? And most molecules do have this little bit of freedom, but the amount of freedom, the amount of change, the amount of tolerance that electron density has based on what's in its environment, what's surrounding it, is a property that can help us tell how strong these forces will be. So all it takes is one hydrogen molecule randomly experiencing this to affect all surrounding molecules. Some molecules are more influenced than others. That's what we call their degree of polarizability that I wrote on the top of this slide. Okay, I know this is pushing things a bit beyond what most students are comfortable with. It's a new idea. But you just got to get around the idea that electron density is free and fluid and changing over time and probability based. Okay, let's move on. Also, I wanted to mention Veritasium has a very good video about London forces where you can see better animations of this and he can explain it well. I forget what it's called and his titles are always changing, so just search Veritasium gecko video. It explains how gecko lizards can walk on walls and windows and ceilings. Okay, so we've discussed this. Some points about instantaneous dipoles then. They appear randomly due to quantum fluctuations, position and density of electron and negative charge. They can influence nearby molecules to generate their own induced dipole. So an induced dipole is not random. It's been caused by a nearby instantaneous dipole. The net effect of this is an attractive force between the molecules. The attractive force between two small molecules, such as hydrogen, is actually very weak. For larger molecules with more electrons, more polarizability, and closer packing, the force may be considerably stronger, and we will see this. London forces actually can become stronger than almost any other force because they just rely on basically fluctuations of electrons. So if there's more electrons, there's going to be stronger London forces. What else can we say? What affects the magnitude of London forces? Their strength. First, number of electrons, as I said. This is often approximated through molecular weight, and that's just because things that have more protons generally have more electrons in their neutral state, because they have to be balanced out to be neutral compounds. And more electrons means more chances that they are going to bunch up somewhere, create a little dipole, an instantaneous dipole, and induce dipoles in things around them. Size and volume of the electron density area, and the ability of electron cloud to be manipulated. That's the polarizability, the electron density. These are huge factors in London forces and their strength. So, larger volume, I think, and higher polarizability, so more chance to spread around that large volume, lead to stronger London forces. Shapes of molecules are also important. How close can instantaneous dipoles approach each other, or induced dipoles approach each other? And shapes will highly affect that. I'll show you on a following slide. So here are some actual data and evidence of what's going on here. F2, Cl2, Br2, I2, these are all the halogens, the group 17 diatomic halogens. So you can see their boiling points, minus 188.1 Celsius for F2, minus 34 for Cl2, 58, plus 58 for Br2, and 184.4 for I2. So these four, pure elements really only have London forces, okay? They don't have any of the other types that we'll talk about today or the next video. But just based on this, you can see that they're boiling points, and therefore it's an estimation of the forces of attraction between these particles, these molecules. Because when it takes more energy to separate them, that transfers to a higher boiling point. That's something else that you really need to get used to. Higher melting points and boiling points mean more energy required to separate, mean higher intermolecular forces. So we can also say the London force strength, since these only have London forces, goes way up as we go F2, Cl2, Br2, and I2. And the reasons are mostly what I said on the previous slide. Many more electrons as you go down the periodic table. Cl2, Br2, and I2 has a ton of electrons. They also have much larger radii, volumes where the electrons can be spread around. So more electrons means that each one is less attracted to the nucleus overall. They're more shielded by things underneath them as well. And it is more responsive to changes in the environment, more easily induced to move around. Larger volume and easily manipulated electrons increase induced dipole formation. Boiling points in these nonpolar molecules indicates London force strength. All very important points. Okay, moving on. What are the effects of distance? So we will not go into that many mathematical details of London force calculations to find its magnitude, but they will follow a proportionality generally that I think we should know. That is the force, and therefore the energy and boiling point and melting point, is proportional to 1 over r to the power of 6, where r is the distance between the molecules, the center of the molecules. So you might remember 1 over r squared, which is what we did for ionic bonding, the relationship between the force and ions. This one is different. They're not permanent ions. They're weak, instantaneous, and induced dipoles. So instead of 1 over r squared, we have 1 over r to the power of 6. What does that mean? That means you need to get much closer. This is significantly more dependent on distance between the center of each molecule to feel the same force, right? To achieve the same force, London force requires molecules to be much closer together. And most of the time they won't get that close, which is why these forces are generally weaker. But anytime when you could get them closer due to their shape or due to some material property in the environment, you can increase London forces greatly. So we have these connections. Larger molecule size generally means more electrons, more polarizability, stronger London forces, more energy needed to separate, and higher boiling point or melting point. General trend is that larger molecules have stronger London forces, which will often be written as LDF for London dispersion forces. Now the opposite is true. If the molecule is smaller, you're going to have generally lower boiling melting point, less energy needed to separate, weaker London forces, lower polarizability, less electrons. Those are associated with smaller molecular weight and molecular size. So some examples: propane, C3H8. It's a chain of carbons and bonded with hydrogens. So its boiling point is minus 42.5, pretty low. It's a small molecular weight non-polar molecule. But when we get up to octane, we've added 5 more carbons along this chain. Just from that, the boiling point goes up more than double to 125, almost triple, I guess. Pretty much is triple. Why? Well, it's mainly because there's now more electrons. There's a bigger volume where the electrons can be in this whole molecule. They're more affected by instantaneous dipoles, polarizability, and induced dipoles, so they're going to be attracted to each other. And the shape of octane is actually very good at approaching other octane molecules. I'll explain that in the following slide. So that's a big difference, mainly due to size. Now we can look at shape. So here we have 2,2-dimethylpropane. This is C5H12. So it should be somewhere in between octane and propane, and it kind of is. Boiling point 9.5. You can see the shape there on the right. Versus pentane, C5H12. So that has the same formula, but it has boiling point 36.1. Quite a bit higher, 20 degrees higher. That is highly significant. Why is that? These have all the same molecules, pretty much the same bonding, same non-polarity. Well, it comes now just from their shape. Okay, for things to experience strong London forces, they need to be able to get close, and that often means stacking. Okay, so let me show kind of how it works with pentane on the bottom. One, two, three, four, five. Okay, so you can imagine these corners are carbons and there's hydrogens attached. I'm not going to draw them all, but pentanes are able to stack up with each other. There's a big surface area where you're going to have intramolecular forces happening, London forces, induced and instantaneous dipoles. That is enough to increase this boiling point 20 degrees. What happens if you take 2,2-dimethylpropane and try to do this? Basically, this looks something like this if I just don't draw the hydrogens and I take each corner as a carbon. Well, this is kind of like in a bubble here, right? If I have another one approach, these pointy carbons stop them from stacking up. They're only going to be able to feel intermolecular forces, maybe a little bit between a couple carbons here, but they can't stack nearly as well as a long chain can, just because of their shape. Okay, hopefully you follow me on that. More surface area that can be in contact leads to stronger London forces. So things that are sort of packed up and spherical don't have as much surface area available and have weaker London forces. Some warnings about London forces then. London forces are not related to gravity. Sometimes I have students say that they think, mass attracts mass, that's gravity, so molecules attracting molecules is also gravity. There will be gravity, but the effects are so insignificant compared to everything else going on that we generally don't consider gravity, and it's definitely not the cause of London forces. London forces occur between all molecules and atoms. London forces are usually not the dominant force for molecules which have permanent dipoles or hydrogen bonding. These are other types that we're going to talk about later, but we have to remember that everything we move on to talk about in the future also has London forces happening underneath the other forces. These instantaneous dipoles and induced dipoles can happen in basically anything that has electrons in it. So maybe something like H+, a proton, doesn't have London forces, I think, but anything with electrons certainly can. So let's move on to dipole-induced dipole forces. This is very similar to what we just looked at. They're the same as London forces in every way, except that the starting trigger is a polar molecule rather than a nonpolar one. So previously I showed hydrogen, H2, a nonpolar molecule, suddenly randomly gaining an instantaneous dipole due to quantum fluctuations. But with dipole-induced dipole, we don't need that. We have a permanent polar dipole on a molecule, for example, water, which I'll show you in my animation here. And it can influence nonpolar molecules around it to get the induced dipole part of this name. So oxygen dissolving in water is an example of this. You guys might know that there's dissolved oxygen in rivers, creeks, lakes, the ocean even. And yet, oxygen is nonpolar. How does it dissolve in the very polar water? Well, the net effect is similarly weak to London forces, but you still can have a little bit of interaction, and that's why a little bit of oxygen gas can dissolve in water. Let's see if I can play my animation to show this. As the oxygen O2 approaches an H2O molecule, it isn't polarized at all at the start. It's a nonpolar oxygen, but as it approaches H2O, the electron density will move in certain ways. So O gets closer. As it gets close to the positive region of water, suddenly it gets polarized. The electrons move to the left side of that O2 molecule because they're attracted to the positive electric field of the permanent dipole on H2O. And that makes the other side of the oxygen positive. Electrons run away from the right side. They run towards the left. And the net effect of this is that as these molecules get close together, there is an attractive force because there's a negative region on O2 and a positive region on H2O. This is enough to bring them together and allow them to mix and allow O2 to dissolve in water slightly. But the concept is very similar to before. An instantaneous dipole generating an induced dipole. Only difference here is that this can happen probably more frequently because we have a permanent dipole on H2O. Okay, that brings us to dipole-dipole forces, which are again similar as before. This time we don't need to induce anything at all though. We just have two permanent dipoles. Dipole-dipole forces are the attractions between two permanent dipoles in molecules. So now, this time imagine we have two H2O molecules. They are approaching each other. Well, what's going to happen is that they're going to orient themselves. They're going to arrange themselves in certain ways to satisfy their electric fields, their electrostatic attraction. So this negative region is going to start to turn because it's attracted to the positive region of another H2O. Okay, it's going to arrange itself so that its positive region is far away from the positive region on the left. Generally, this is what we call dipole-dipole forces. So you can imagine in the end, water molecules all arrange themselves so that positive is near negative neighbors regions, negative is near positive regions of neighbors. Okay, I don't really have much more else to say about that other than this can happen much more easily because all the molecules have permanent dipoles and they're a fair bit stronger than London forces as long as the molecules are still fairly small that we're talking about. So here's some more data. Compound ICl versus Br2. So these are again group 17 elements, all of them. One of them is a compound, whereas one is a pure element though. So Br2 pure element has no dipole, no permanent dipole. It has only London forces. Its boiling point is 58.8. Types of intermolecular force, London only. But ICl has a permanent dipole. Cl is more electronegative than I. The electrons are held more closely by Cl. And so they can arrange themselves in a gas or a liquid or whatever, where negative regions are near positive regions. They offer sort of permanent attractive forces that really increases the boiling point to 97.4 for ICl. Types of forces involved though, remember that there's still London. London probably makes up a large part of the attractive forces. Maybe that would bring the boiling point up to 58 roughly, but it's the dipole-dipole forces that pushes it 40 degrees higher. That's a good way to think about it, I think. Okay, what else? So yeah, we can finish today with just a bit of practice. Which of the following compounds experience dipole-dipole forces? O2. Does this experience dipole-dipole, permanent dipoles on the molecules? I think you'll find it does not. You can draw it quickly, but O2, Lewis structure is like this. There is no net dipole. The double bond electrons are held perfectly 50% between each oxygen. No dipole on that. Okay, what about CO2? I think you'll find a very similar situation. So these are polar bonds. C double bond O, C double bond O, with a couple of lone pairs. Very polar bonds. Oxygen is more electronegative. But these vectors are equal and opposite. One goes left, one goes right. The net effect is that there is no dipole on this CO2 either. So it will not have dipole-dipole forces for sure. Only London. Carbonate, C. Oh, okay, this is a bit of a dirty question to give to some students because it depends, I think, whether you've studied HL or SL. The answer might be different. Since I'm doing an SL video here, I can show you generally this structure frozen in time could be considered to be polar. You've got negative charges near one side of the molecule, here and here. So the effect is the bottom of the way that I've drawn this structure would be very polar. Delta negative pointing down there. So in that case, it could experience dipole-dipole forces. But if you're in HL, you will know that the double bonds and negative charges actually average out through this molecule in such a way that all the vectors cancel out, and it is not polar. So, no for HL students. If you studied resonance, you should know this. And SL students, it can't help to learn the truth. A little bit of extra knowledge there. Okay, carbon monoxide, CO. This is D here. This will certainly have a dipole. It's just carbon triple bonded with oxygen. So those can arrange near other CO molecules and generate dipole-dipole forces. Okay, and then number 2, draw a depiction of how propanone, CH3COCH3, molecules might arrange themselves when near each other. Use dotted lines to show intermolecular force attractions. So propanone, I'm just going to draw a skeletal structure. It's time that you get used to seeing this anyway. I've been using it earlier in the video as well. So skeletal structure for propanone looks like this. CH3 on the left, C double bond O in the middle, CH3 on the right. So oxygen being much more electronegative will push the vectors and the dipole of this upwards, the way that I've drawn this here. So if another propanone is nearby, they will arrange themselves like this. Because the bottom is a positive region and the top is negative, right? So the same would be true here for the top propanone. Positive bottom, negative top. So we're going to have a bit of dipole-dipole interaction between propanone molecules. And it probably won't be just two, it'll be millions arranging themselves based on what's nearby. And offering a bit of attractive forces, it's going to increase the boiling point higher than you would expect just from London forces. Okay, hopefully that helped. Hopefully you got some good ideas about what London forces, dipole-induced, and dipole-dipole forces are. Next time we'll look at hydrogen bonding, one of the most consequential types of intermolecular forces because it's the main one that water has, and it affects a lot of things around planet Earth and life on Earth. And then we'll do a bit of a summary or recap of all the forces together and how they might work together. All right. Thanks for watching. See you guys next time. Bye-bye.